Hello everybody. Thank you very much for introducing me. It's a great honor to be here. And especially since I was taking courses here at this very lecture room by 최우진 교수님, 구자경 교수님, and 김동수 교수님, and all these professors. Special honor to be in front here giving lectures. So today I'll talk about Ramsey numbers of graphs, and I will try to make a gentle introduction to what it is, first the definition of Ramsey numbers, and slowly go towards my recent theorem. So it will, it's meant to be an overview on Ramsey numbers, so please interrupt me if you don't understand something. I will assume that you know very basics on graph theory. Okay, so what is Ramsey theory? Ramsey theory, very informally, can be defined as the study of problems that can be grouped under the common theme, saying that every large system contains a highly organized subsystem. Of course, this is not a very mathematical statement, but this captures the spirit of theorems studied under Ramsey theory. The classical example is the following theorem of van der Waerden from 1927. Well, he was actually a number theorist, and this is the only theorem he studied that has combinatorial flavor to it. It says, for all integers, all natural numbers k and r, there exists an integer n, which depends on these two numbers, such that the following holds. If such that in every r coloring of the integers from 1 up to n, there exists an arithmetic progression of length k, whose all elements have the same color. And this, in other words, I will say a monochromatic arithmetic progression. So let's say I want to find a 100-term arithmetic progression. So 1, 3, 5, 7, up to 101. And then somebody gave me a number, let's say 5. Then I can give you a number which is very large, like, I don't know, 100 million, where if I color the integers from 1 up to 100 million in 5 colors, then no matter how we color it, there exists in one of the colors I can find the arithmetic progression of length 100. Okay, so this is a spirit. So this is a typical theorem in Ramsey theory, and it motivated many future results that had great influence, not just in combinatorics, but also in mathematics. So the two famous examples are Degenerate theorem, again an arithmetic progression in dense subsets of integers, and that result gave Degenerate the Abel Prize a few years ago. And the more famous example is Green-Tau theorem on arithmetic progressions in primes, which gave Terry Tau his Fields Medal in 2006. And this result can be seen as one of the motivating theorem behind these work. Okay, so today I would like to focus on graph Ramsey problems. So you'll not see any arithmetic progression anymore, but even graph Ramsey theory is closely related to this. I won't be able to talk about the connection today, but if you're interested in, then I'll be happy to tell you more afterwards. Okay, so for some notation, I let Km be the complete graph on n vertices. Meaning a K3, I have 3 vertices all connected to each other. K4, 4 vertices all connected to each other, and so on. So here's the most important definition for today's lecture. So given two graphs H1 and H2, I define the Ramsey number of the pair H1, H2 as following. I denote it as R of H1, comma H2. This is the minimum integer n, or minimum natural number n, such that in every red-blue edge coloring of Kn, there exists either a red copy of H1 or blue copy of H2. And for another notation, if H1 and H2 are the same, these are said as to be diagonal cases. I just say R of H instead of R of H, comma H. And this is known as the Ramsey number of H. So let me show you an example. Let's start with a very easy example, R of K2, K3. So we have two colors, conveniently red and blue. So I want to find a red K2, that is two vertices connected by an edge, or a blue K3, three vertices pairwise connected by edges. Now, to find the Ramsey number of this pair, I have to show you two things. I have to find a coloring of the complete graph, which avoids both of these shapes. And then I also have to show that if I have more vertices, no matter how I color it, one of these shapes will appear. Let me make it more precise. So, proof. First is I will show that R of K2, K3 is greater than 2. So there exists a coloring of two vertices, avoiding both shapes. That's easy. Just take a blue edge. I don't have a red edge, I don't have a red triangle. On the other hand, R K2, K3 is at most 3, because if you have three vertices, I can never use the color red. If I use it for a single edge, I will just automatically have this shape. That means automatically all colors have to be blue, but that forces my second. So I'm dead. I just can't do anything. So this is a small case. It's just quite easy to see what's going on. Let me do one more case. R of K3, K3. And this is equal to 3. Because 2 does not force one of these copies, but 3 does. K3, K3 is known to be 6. So again, the first case I have to show that it's greater than 5. I have to give you a coloring of 5 vertices. And that's a famous coloring. Okay, so all pairs I colored by red and blue. Red are blue, and I can't find a red triangle or a blue triangle. Neither of these shapes exist in this picture. What about for 6 vertices? Now it's not as clear as this one, but once you've seen it, it's quite easy to see what should happen. So fix one vertex. I have to show you no matter how you color it, there exists a red triangle or a blue triangle. So let's just say I just look at the edges incident to this vertex. There's 5 of them. By pigeonhole principle, at least 3 has to be of the same color. In this picture, I have 3 blue neighbors. So let's just focus on these 3 vertices. Now, if at least one of them was a blue edge, I already have a blue triangle. That means I cannot use a blue edge at all. I have to use all of them with a red. That forces a red triangle. So this argument is quite simple. It establishes that R K3, K3 is equal to 6. And you might have noticed that I actually used this argument inside here. So what's going on inside the neighbor was exactly what's happened in the previous example. So you'll see this again. But before doing that, okay, so I will have to write down another thing. Actually, let me write it here. Our K2 is trivially 2. Our K4 is known to be 18. So let me write the next case. Okay, I can't show it. It's not as simple as this one. But what's more surprising is R of K5 is not known. There's only a range of parameters, lower bound and an upper bound, which bounds our K5 into a certain interval, but we cannot pinpoint the exact number of what our K5 is. Actually, this is our K4. Our K5 is between 43 and 49. I'm not saying that computing these exact Ramsey numbers are very important problems in mathematics, but we're trying to understand what's going on in this Ramsey number definition. And already, for such a small graph, it gets out of control. And people quickly notice that this Ramsey number gets out of control. It's a really difficult function to compute. So there's a famous quote by Erdős saying that the following. So suppose aliens invaded Earth, right? And they threaten to kill all people on Earth unless you can compute R of K5 precisely. In that case, we should use all resources on Earth to try to compute it. We can probably do it. But if they ask for R of K6, we should prepare for war. Okay? There's no way we can compute it in 1 year, even if you use all the resources on Earth. So there's no rigorous proof of this fact, but computationally people believe it's a very, very difficult problem, and there are many evidence towards this. Okay. So that was kind of the introduction. The study of Ramsey numbers of graphs, it first started in 1930, and it was started by Frank Ramsey. He was interested in a variety of topics, and he was actually first interested in this number. He introduced it because it had application to some problem in formal logic. So still, Ramsey's theory lies as a connection point between combinatorics, logic, and combinatorial geometry and many areas. So it started in 1930. In 1935, let me write down the history. Erdős and Thekerish found geometric applications of Ramsey theory, and actually they contributed a lot in popularizing Ramsey theory to a broader audience. So one of the results in their paper is the following proposition that gives general upper bounds on Ramsey numbers of pairs of complete graphs. So they prove that for all natural numbers t and s, the Ramsey number of kt, ks is at most the Ramsey number of kt minus 1, ks, plus the Ramsey number of kt, ks minus 1, giving a recurrence relation for Ramsey numbers. So this immediately implies the following useful bound. At most t plus s minus 2, choose t minus 1. Let me show you this proposition. And most of you can reconstruct it already if you study these two examples carefully. So to prove the proposition, I will let this number be n. I have no idea what it is, but just to simplify the notation, let me call it large n. I have to show you that no matter how you color the edges of the complete graph on n vertices, using red and blue, there has to be a red complete graph on t vertices or a blue complete graph on s vertices.
Shouldn't make n be the right hand side of it?
Yes, you're right. Thank you. Let's make it the right hand side. Thank you. So what's going to happen here is I take a Kn. There's a lot of vertices. Somebody gave me a red-blue coloring. How I'm going to find a KT or a KS is first fix the vertex, just like here. Look at its neighbors. So there are either at least R KT minus 1 KS red neighbors, or at least R of KT KS minus 1 blue neighbors. Simply because the number of neighbors of V is exactly R of KT minus 1 KS plus R of KT KS minus 1, because we're excluding one vertex, then one of these must hold. Depending on which one holds, something like that will happen. So let me just assume that the first case holds. If first case holds, then in the red neighbor, there exists a red KT minus 1 or a blue KS. What's happening is there are a lot of red neighbors. Inside here, I will either find a red complete graph, T minus 1 vertices, or a blue complete graph, S vertices. If I have this, I'm already done because I'm looking for a KS, blue KS. In this case, just add the vertex V back in. Then instead of T minus 1, I have T vertices all connected to each other by red edges, giving a red KT. And you can use a similar argument to the second case as well. So really, it's just this argument, again, applied to abstract numbers instead of concrete numbers. Okay. So let's try to digest the meaning of that proposition. Since we've been focusing on the diagonal case, meaning when the two graphs are equal, for large T, what they proved is essentially R of KT is at most 2T minus 2 choose T minus 1. And very roughly, this is not the right notation, but it's like 2 to the 2 T. So we can give an exponential upper bound on the Ramsey number of complete graph on T vertices. Recall that this is KT, KT. What about a lower bound? Can it really be an exponential behavior? And that question has only been answered after 12 years. So in 1947, the date's there, Erdős proved that R of KT exponential bound is the correct behavior. So R of KT is at least 2 to the 1/2 times T. Okay? So we don't know the exact exponent, but we can bound it from an exponential function from above and by an exponential function from below. And this proof is really a beautiful proof using the probabilistic method. It's one of the earliest applications of the probabilistic method. I can show you right here how it goes. So I will take n to be 2 to the t minus 2 over t because I know this will work. And so let's see, what do we have to prove? I have to color the complete graph on n vertices using two colors so that it avoids a blue KT and a red KT and a blue KT. So trying to do it really by hand is difficult. The brilliant idea to choose was, let's just toss a coin to do it. So take a complete graph Kn. For each edge, toss a coin to decide red or blue. That means with probability half, I'll take a red color for a single edge. with probability half, I'll take a blue color. And for all edges, make it independent. So I will toss lots of coins to color the graph. How do we even analyze it? So what we want is, we want the coloring with no monochromatic complete graph on T vertices. Okay? So I will define the random variable x as the number of monochromatic complete graphs on T vertices. Let's see what happens. So it's hard to compute. It's not hard to compute the expected value of this random variable. Simply, all I have to do is, by linearity of expectation, take the sum over all subsets A. A is a subset of size T. Subset of vertices of size T. The probability that A is monochromatic complete graph. Okay, so how many subsets of vertices we have? We have exactly n choose T. N vertices choose T vertices. What's the probability that it's monochromatic? It's the probability that all edges have the same color. 1/2 to the number of edges, which is T choose 2. Then we can choose red or blue, so times 2. So then the key point, the punchline here is, with this value of n, it becomes less than 1. And that's it. Because what I proved is, I defined the probability space over all colorings of the graph, and then computed this expected value of this random variable. It turned out to be less than 1. That means there has to be one particular coloring where x is equal to 0, because x is always an integer. Therefore, there exists a choice of coloring such that x is equal to 0, meaning that it does not contain a red or blue complete graph on T vertices. And that's it. So this is a really beautiful argument, such a simple argument, a beautiful argument, giving the correct behavior of the Ramsey number of complete graphs. Now, the reason I went into detail for these two is, even though such a simple proof established these bounds, for the past 70 years, people tried really, really hard to try to improve that 2 in the exponent to r that 1/2 in the exponent. I mean, really hard. All the combinatorics people that I know tried this problem. And really strong people. They are really, really smart and strong. They know all the current techniques and everything. But nobody succeeded. So this 2 and 1/2 just stayed there for the past 70 years. And this is considered as one of the most challenging and important problems in combinatorics. So I hope I was able to announce some progress there, but that's not the case. So that kind of also tells you gives you again why people think Ramsey number is so difficult to compute. Because already estimating it seems to be out of the reach of our current technology. Okay, so what's special about complete graphs? The following theorem kind of illuminates why complete graph is an important case. So it's a result of Sudakov. Let me check the date. Oh, I didn't write down the date. Oh, it was in 2000s. He was proving the conjecture of Erdish and Graham. So it's the following. If G has m edges, then the Ramsey number of G, or let's use H, I've been using H so far, is at most 2 to the some constant times square root m, where C is an absolute constant. So why is this an important result? It's because let's consider a complete graph. M is equal to n choose 2. Oh, sorry, t choose 2. Sorry again. If H is a kt, then M is equal to t choose 2. So this kind of means R of H is at most 2 to the c times square root of t choose 2, which is after some constant 2 to the c prime times t squared, t. Okay? So this shows that the exponential upper bound, or this type of behavior, holds for general graphs as well. And in some sense, complete graph is the worst possible example. Okay? If you fix the number of edges, this is the worst you can get, and complete graphs actually gets that bad. So in that sense, complete graph is an extremal example.
How large is it?
I don't know. I saw it this morning. I think it was 250 around. Reasonable number. Okay, so that was for some diagonal things. But let me mention that Ramsey number can be significantly smaller than this. So that was the first example. If H is just m vertex disjoint edges, this is very sparse while complete graph was dense. For this, it's not difficult to see that the Ramsey number is linear in terms of the number of edges. So RH is at most C times M. Probably can compute the exact constant C here, but just to give you some idea on what's going on. So even though it can get as bad as exponential, there are also graphs where it's far from the truth. Okay, so far I've been talking about diagonal cases. What about the non-diagonal case? Maybe it's easier if we just consider different cases, right? So this proposition, what if S is fixed and t tends to infinity? So as a concrete example, how does R of K3, Kt grow as a function of t? Maybe this is manageable. The other problem was difficult. But because we're just restricting a triangle, that kind of makes the analysis easy, right? And so one of the breakthrough results made by Kim, Professor Kim at KAIST, what he did was he established the correct order of magnitude of this function. So together with the previous known result of Aitai, Kamlosh, and Semeredi, these people prove that R of K3, Kt is at most some constant times t squared over log t. And then Kim proved that R of K3, Kt is at least some constant times t squared over log t. So here we know the correct order of magnitude. And that was considered as a real breakthrough, because people believe that estimating or computing Ramsey number is so difficult. So naturally, one can try K4 Kt. But there already our understanding is pretty bad. The best known bounds are, oh actually, let me give you some perspectives before going into this. K3 Kt, if you apply that proposition, the bound you get is at most some constant times t squared. So this upper bound already improves that kind of easy upper bound by a log factor. So if you apply that upper bound to K4 Kt, you get a t cube. What people know how to do is, so they can divide this by a polylog factor just like here, as an upper bound.
Divide?
Yes, divide. So divide. While the lower bound is already a factor of it. T to the 5 over 2 or some polylog. Maybe divide.
Log, you mean composition of logs? Or
No. Log. I think this is actually t cubed over log t times log log t.
okay.
So some polynomial in logarithmic function. So we don't even know the correct exponent here. Forget about the log. Right? So already K4 gets out of control. Okay. So that's kind of good. What time is it? Okay, 30 minutes, good. Now, excuse me?
T powered by 5 health multiplied by
Polylog. This one? I'm not sure. It might be division of multiplication. So there are some log factors floating around. But sorry, I didn't check it carefully. But the main message I want to say was already the exponent is far apart. So it's probably not very worth trying to fight for this polylog factor. And of course, this is a different story because this really closed the order of magnitude. Okay, so let's try to talk a little bit more about general graphs. Here, we Sudaka kind of succeeded in giving a general upper bound on the Ramsey number of graphs. But as I said, when the graph is really, really sparse, this behavior is far from the correct behavior. Let's try to go into that a bit more in detail. So the probabilistic method proof, this one, if you really carefully analyze it, just apply the same proof to general graphs, gives the following result. If H is a graph with n vertices and m edges, then the Ramsey number is at least 2 to the m over n. There's actually a times 1/2 here, but yeah, it's just cleaner in this form, so let's write it like that. There's a small -1 here. But, okay. So what this kind of says is, Ramsey number will be large if there are a lot of edges compared to the number of vertices. That was the case for complete graphs. Whereas for the second example I showed, collection of matchings, even though it has the same number of edges, it has 2m vertices. So this number is significantly smaller. There's something going on around this parameter. So actually, consider the following bound. If h prime is a subgraph of h, then just trivially r of h prime is less than or equal to r of h. Because if you want a monochromatic copy of h, you must first have a monochromatic copy of h prime. That, together with this, gives the following bound on the Ramsey number. At least 2 to the maximum over all subgraphs of h. The ratio between the number of edges of h prime and, 2 to the number of edges of h prime divided by the number of vertices of h prime. Okay. So what does this mean? This quantity is actually an important parameter in graph theory. It's called the average degree. Meaning, on average, how many edges are each vertex incident to? So define d of h, the average degree, as the ratio between its number of edges and the number of vertices. And this can be rewritten as the maximum over all subgraphs, the average degree of h prime.
You need to know what vector too.
Yes, and 1/2. Yes. Okay. So that kind of motivated Burr and Erdős to make the following conjecture. Let me see one more thing. So the difference between this bound and that bound, it seems like it's not a real big difference, but it can be important because suppose that H has, let's say, 1,000,000 vertices, but most of the vertices have like one edge instituted to it, while there's a small component, meaning component of size 10,000, that's complete. Let's try to do the computation. This is 10 to the 5. This is 10 to the 4. This is 10 to the 6. Number of edges of the whole graph is about 10 to the 8 because all of the edges are focused in here. 10 to the 8 approximately, plus all other edges, vertices have degree 1, so plus 10 to the 6, meaning this will be the dominating term. Number of vertices, we saw it's 10 to the 6. So if you apply the first bound, what we will get is the Ramsey number is at least 2 to the 10 squared. Bound 2, we will just forget about all these vertices, focus on the important part. Here, it has roughly the same number of edges, but the number of vertices is significantly smaller. We will get an order of magnitude 2 to the 10 to the 4th. So the second bound actually does a lot better than the first bound. So this captures also these kind of behavior where you have a hidden dense graph inside a large sparse graph. So Burr and Ergis thought that this was the right parameter that captures the Ramsey number. So for a graph G, the degeneracy of a graph G is the minimum integer. Let me rephrase it. A graph G is D-degenerate if the following holds. All its subgraphs have a vertex of degree at most d. And actually a better way to see it is, this implies that all subsets X contain at most d times x edges. Okay. So given a subset, just take out vertices of minimum degree 1 at a time. Each time we remove at most d edges. We can repeat it x times, so we have at most d times x edges. So you should think of d as a fixed small number, like 100, and the number of vertices grows like 10 to the 6 or even larger. So what this means is that the whole graph is extremely sparse, and there is no dense component like this. Because really, now that parameter, maximum over if G is D-degenerate, then the maximum over all its subgraph of d of h prime is actually at most d. Now this is an interesting class of graphs, especially in terms of that bound, because if you just apply that bound, the best we get is 2 to the d. And I said d is a constant. So let me write it here. For D-degenerate graphs, R of, again I use G, is at least 2 to the d. Let's say minus 1. You might think that's a useful bound, but that's a really stupid bound. D is a fixed integer, and G can have a lot of vertices, so it's better to use a trivial bound that Ramsey number is at least the number of vertices of G. Right? Because this can be a huge number, that's a fixed number. Now, that's probably why Burr and Erlich made this conjecture. 1973. It said if a graph is degenerate, then Ramsey number of G is at most some constant times the number of vertices of G. So for all D, there exists a constant C such that the Ramsey number can be controlled as a linear function in terms of a number of vertices. And this is really there's a big difference between this and complete graphs, because for complete graphs you expect more like an exponential behavior in the number of vertices. Now, because it's sparse, probably this behavior takes over the exponential type. And that's at least what they believe to be true. And so this conjecture actually gained quite a popularity since then. And it was one of the main driving forces behind many important tools in extremal combinatorics and probabilistic combinatorics. So the first partial result towards this conjecture was made by Quattal, Rodel, Semerity, and Trotter. So partial results. 1983. Quattal, Rodel, Semerity, and Trotter prove that for all D, there exists a constant C such that if G has maximum degree at most D, then the Ramsey number is at most C times the number of vertices. Okay, so they weren't able to prove it for the case when graph is degenerate, but instead for a weaker notion of sparseness, namely when the max degree is bounded, they were able to prove the conjecture. The technique is by now quite standard, using the regularity lemma and the following embedding lemma. But actually, this was one of the earliest application of the regularity lemma to graph theory, other than the original application by Semerity. So the theorem that I mentioned in the very beginning, van der Waals theorem on monochromatic copies of arithmetic progressions in integers. So in some sense, it's really closely connected to this result, because the development made in that direction actually created a very powerful tool that can be applied to this. And that tool, it's really amazing. And I can't show you what it is, but I can show you why it's amazing. Because this constant, so this constant depends on D. They prove that the C is finite, depending on D. But what they proved is C is at most 2 to the 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 2 to the. This is about like D to the 5 or something, or even more. Okay? And this is a typical behavior when you apply regularity lemma. So we're not surprised anymore when we see this. But you can understand, people were like, this can't be true, right? That can't be the right behavior. Though there are a lot of interesting stories behind it. I won't go through in detail. So later, people were able to get rid of that tool and just directly prove this result. So first improvement was made by Eaton. He proved that the constant is at most double exponential. Oh, it's so small compared to this, right? It's tiny. And then, who was it? Rodel, Semerity, Graham, Rodel, and Rutchinsky. Graham, Rodel, and Rutchinsky improved it to a single exponential. And, not single exponential was the log square factor. And then Conlon, Fox, and Svirakov improved this to, they got rid of one of the log factors here. Okay. So that's the current state of art. On the other hand, it's known that they are, there's C prime. It's known that there are graphs where the C has to be at least exponential in D. So this behavior, they got the state of art is pretty close to the best possible bound. What are some other results? I don't. Chen and Shell. Okay, in 1993, these developed. This is in the 90s. These are in the 2000s. And this one is 1993. So Chen and Shelp, 1993, proves that conjecture is true for planar graphs. And planar graphs are known to be degenerate. In fact, they proved it by proving the conjecture. In fact, proved it for arrangeable graphs. I won't define what this is. Just think of it as a measure of sparseness that lies strictly between max degree and having bounded degeneracy. So one step at a time, we're getting closer and closer to the conjecture. So basically arrangeable graphs was kind of the limit on how far we can attack this conjecture using the currently known tools. For some reason, degenerate graphs, these tools didn't apply to degenerate graphs. For degenerate graphs, the first breakthrough was made by Kostachka and Rodel in 2004. So they weren't able to prove the conjecture, but they proved that Fg is d-degenerate. Then the Ramsey number is at most some constant times n squared. So they proved the number of vertices square. They proved a quadratic bound instead of a linear bound. And then the second breakthrough was made by Kostachka and Sudakov. And this is an especially important result for me because actually the dates are messed up. This is a result after this. But this journal is a lot slower than this journal, so it's flipped. So after 2004 and 2003, we proved that Ramsey number is at almost linear. So function is not very pretty. I'll first write it as 1 plus little o of 1, meaning that it's almost linear. And the exact bound they proved was e to the c times log n to the d over d plus 1 times n. So this is sublinear, but it goes to infinity as n does, giving this n to the 1 plus little 1 type behavior. And they kind of pioneered this tool known as dependent random choice, which turned out to be a really powerful technique in this area. So later, Fox and Sudakov in 2009 went further with this technique. Slightly further because they improved this dependency. They got rid of the d dependency. So R of g is at most I don't need to even see here. E to the c log n to the 1/2 times n. Square root.
It's the number of places.
Yes, n is. Thank you. Okay.
Where's D? So C out.
C depends on D now. Yes. And so I was able to build on these results and settle the conjecture. So my theorem is the following. If G is a d-degenerate graph, so there exists an absolute constant C such that if G is degenerate, then the Ramsey number of G is at most 2 to the 2 to the C times D times the number of vertices. So the constant is double exponential in the degeneracy, and it's linear.
Absolute constant means that it doesn't.
Oh, this does not depend on D.
Not only E but also G.
Not even G. Yeah, so not depending on G is very important.
How big is C?
I haven't tried computing it.
Is it really big or is it reasonably big?
Reasonably big in the sense that probably less than 1 million.
Less than.
Yes. In this business, double exponential is not too bad, as I said. So, as I said, double exponential is not too bad, but it's not best possible. Well, at least not known to be best possible. So, it's known that the following graph, k, d, n minus d, just meaning d vertices on one side, n minus d vertices on the other side. This is known to be degenerate, d-degenerate. And the Ramsey number of this graph is roughly at least 2 to the d times number of vertices n. And as far as I know, this is the best example. So it's still, there are some room for improvements between these two bounds. Can we understand better the Ramsey number of d-degenerate graphs? Toward that direction, there is a more finer theorem than this, if you know the concept of chromatic number. So if G is additionally R colorable, then Ramsey number is at most 2 to the D times 2 to the C times R number of vertices. So if you have a fixed chromatic number, we know that a single exponential behavior is correct. So let me just define chromatic number. R colorable means graph is R colorable if there exists coloring of vertices by R colors, so that no edge has both of its endpoints same color. And for those who've never seen chromatic number before, this sounds like a very childish definition, but it turns out to be a really, really important parameter in graph theory. And as you can see, for somehow coloring of vertices is related to these type of behaviors. And there's a lot more surprising behaviors around that. Okay, so that's pretty much it. I just want to say a few words before finishing. So I'm generally interested in just embedding degenerate graphs into larger graphs, because it seems like the known tools so far developed are not powerful enough to handle degenerate graphs as opposed to graphs of bounded degree. And it seems like the tools used here, which is based on previous developments, have some potential to push forward several previous results that were proved on maximum degree graphs, or weaker notion of smartness. So my future plan is to try to push those theorems further and extend those theorems to degenerate graphs and try to understand better. So that's it for today. Thank you very much for listening.
Thank you. Do you have any questions?
Do you think that there is a hope to find the universal constant D in the per-Erlich conjecture?
C, you mean?
C.
C, so know the exact behavior? No. So I think you might, maybe with a lot of luck, you might be able to show that single exponential behavior is correct. I think it should be single exponential. But determining the exact constant will be probably impossible. As difficult as determining the Ramsey number of graphs. Just complete graphs.
That is solved the conjecture.
Ah, yes, that solves the conjecture.
Any other questions? So what is the major new ingredient that you added?
So one of the main new ingredients, so I really heavily rely on the tools developed here, is, so there is this tool called dependent random choice that was started to be developed around 2000s and is still being under development. And I realized that you can add a weighting scheme to it. So actually, I wasn't even planning to attack this conjecture. It seemed like out of reach. But then there was a toy case, so an easy case suggested by Fox and Surakov in this paper. They said, try this easy case first, because it seems like it captures all the difficulty while looking more simple. And so at some point I started thinking about it on my way back from Atlanta to Boston on some plane. I had some idea, I tried it, and that toy case worked using just one simple additional idea. And then if you know this enough, with that idea you can push it. So if you know the previous tools well enough, that additional idea will take you all the way.
So when was the trip? Last year or?
This spring.
This spring. Okay, that must be good. Right. Any other questions? Or? Yeah, so if not, let's thank the speaker and